This conference will now be recorded. This conference will now be recorded.
Very good evening, students. Today we'll be continuing with discussions on alternating current chapter. So here today in our discussions we'll be learning about phasor diagram, and we'll see the current and voltage relationship using phasor diagram and analytically also. When AC signal is sent through a pure resistor and a pure inductor and a pure capacitor. Okay, so that is our aim today to complete. So let us start our discussions. See, what is phasor and why do we need this phasor diagram at all? See, we have in general we have seen in DC circuits we may have resistor, we may have capacitor, okay, we may have inductor, we may have these circuits in AC also with this, okay. So with this, when we send AC signal, this is resistor, this is capacitor, this is inductor. When we pass AC signal in a circuit containing resistor, capacitor and inductor together, or any of two, at least multi-component. So these are called electrical component. This resistor, capacitor and inductor of inductance L, capacitor of capacitance C. These are some electrical components. So when we have multiple electrical component in AC circuit, so DC circuit we know what it happens. Transient phenomena we have discussed already, or maybe we'll discuss again in this chapter itself. So in case of AC, what happens? So when we send AC signals, see, one thing you might be noticing that this symbol is actually for AC signal, AC battery or AC signal. I'm not giving any sign because this AC signal generally changes its sign, changes its direction continuously, as we have read in the previous class. So I should not give plus or minus, something like that. Okay, we should not give this because plus minus is not constant here. Direction changes continuously. Sometimes current will pass through this way, sometimes current will actually emit from this source this way. Okay, all right. So when we have multi-component in AC circuits, then how to find out the current through the circuit? That is one way. See, one reason how to find out the current. Okay, and what are the interrelation or relation among the voltage and currents in each components? So that thing we can easily understand graphically. Okay, we can easily understand the current voltage relationship in a circuit or through circuit elements when we have multiple circuit elements in an AC circuit. Okay, when we have multiple electric element like resistor and capacitor, or inductor and resistor, or capacitor and inductor, or maybe all together. All together can have parallel combination, we can have series combination. So this is actually series combination of LCR. Okay, series combination. So when we have multiple electrical component in an AC circuit, how to find out or visualize the current voltage relationship in the circuit? Current in the circuit and voltage across each component, how they are related to, like how they are related. So that thing can be easily understood graphically. Okay, graphically, and that is actually Phasor diagram method. That is actually Phasor diagram method. So here what we do generally, Phasor means what? It is actually a rotating vector. What is a phasor? Phasor is actually a rotating vector. A rotating vector that represents sinusoidally varying quantity is called a phasor. What is phasor? It is actually geometrical constructions. Okay, this is geometrical constructions. So phasor is a rotating vector. Rotating vector. A rotating vector which represents a sinusoidally varying quantity or alternating quantities. Alternating signals, or signal means voltage or current. Alternating current or voltage. Current or voltage. Okay, is called a phasor. So you might be thinking, what is this? A rotating vector. This is actually a concept of physics. This is graphical representation of, see, phasor is actually graphically represents, it is actually a vector but not a real one. This is not a, phasor is not a physical quantity, but this is a geometrical or imaginary quantity which has a direction and magnitude. Okay, direction, particular direction and magnitude. So that's why it is actually a rotating vector, which represents a sinusoidally varying quantity or alternating quantities, alternating current and voltage. So that is actually phasor. Okay, so I think I have to just remove this to show you a figure about rotating vector. See here, suppose this is a rotating vector. Okay, this one is a rotating vector. Suppose I give a name OA. OA, this tip is A, this is O. So OA is a rotating vector, and you know this rotating vector can rotate all the way through 360 degree. Okay, it can rotate all the way through 360 degree anti-clockwise. See, if I suppose I have a voltage V is equal to V0 sine omega t, or here it is given as current. Let me just take the current itself. Suppose in a circuit the current is varying like this. See, I is equal to I is equal to I0 sine omega t. Okay, so this is suppose alternating current which is varying as I0 sine omega t. So here we know this is instantaneous value. That means at any instant of time we can get the value. If we just put the time instant, suppose t1, t2, t3, then I will get instantaneous current I1, I2, I3, etc. But I0 is actually the amplitude, the maximum value of this quantity. Okay, maximum value plus or minus I0. Okay, so fine. So here if I want to represent this current, alternating current with a rotating vector, then I have to choose a rotating vector in such a way that the magnitude of this vector, suppose this OA, this magnitude should give you the value of this I0. And if we take the projection, suppose the variation of the current in the vertical direction. So we have, if we take the projection of this rotating vector OA on the vertical axis will give you the instantaneous value. As you see, this much is instantaneous value, because it changes its value. See, at this particular angle omega t, it has this value. Okay, I can go some other angle. Okay, then instantaneous value will change, right? I can be here also, so instantaneous value will change. So it changes with instant. Okay, omega t, with this omega t value, if I just say this is omega t, so with omega t, I'm sorry, this is not omega t, just t. Okay, so with this t, actually with the instant, with each instant, like at each instant it has a different value because projection is different. See, this one, like that. All right, so what I'm trying to say is that any sinusoidal quantity can be represented by a rotating vector, but to represent that particular quantity by rotating vector, we have to take a rotating vector which has a magnitude equal to I0, and whose projection will give the value of instantaneous current at each instant. Now this rotating vector has to be rotated. Rotating vector has to be rotated anti-clockwise with the same angular speed as the alternating quantity is changing or varying. Okay, that means here see, omega is the angular frequency of variation of this current. So I have to actually rotate this rotating vector in this particular frequency itself, angular frequency itself. If this is, suppose this is some omega 1, then I need to rotate this rotating vector with omega 1 angular velocity. So you'll be surprised to know one thing is that, see, I have, yes. So suppose you want to consider a full cycle. See, you can just rotate the rotating vector, by, see, 30 degree, 60 degree, 90 degree, 120, 150, like that. If you go up to 360, you can generate a full cycle of that particular AC signal. Okay, if it is current, then you'll get the full, like I0 sine omega t, I is equal to I0 sine omega t for a, sine omega t for a full cycle, for a complete cycle. So this is actually t by 4. See, this is t by 4, this is t by 2, and this is 3t by 2, and this is t. Okay, so you can generate the whole, like for a complete, for one cycle you will get complete, see, complete cycle of this signal. As we have seen sinusoidal variation in the previous class. Okay, alternating current should vary, actually its magnitude and direction should vary periodically. So here we had learned that sinusoidal variation is the ideal variation for or best variation for alternating current or voltage. So here, look, the projection on the vertical axis, see this projection on the vertical axis is this much value at 30°. This is the instantaneous value. Okay, this changes, whereas this magnitude is always constant because it is just rotating on a circumference. Okay, circumference uh, of the circle which has radius OA. All right, so here our magnitude the same. Okay, magnitude is same everywhere. That is what actually this also represents. This represents that the magnitude, maximum amplitude is the same. So here, see, at 60°, 60° projection is here. Projection here. So this particular point will get 0 will get this particular point. Okay, 90° will get this particular point. Then 150 will get again this, 120 will get this point. Okay, 180 will be this. Then it will go below at different angles as you have taken. See, at 0. Then we can just connect this line like this. Okay, we can connect this and we get a full cycle of that particular this current. Okay, full cycle variation of alternating current I is equal to I0 sin omega t. Okay, so this is what is the power of rotating vector or phasor diagram. So here you look, what is phasor diagram? See, a diagram that represents alternating current and voltage of the same frequency as rotating vector or phasors along with the phase angle between them is called phasor diagram. I mean to say, suppose in a circuit we have just resistor, we will see that if we have just resistor, so the current and voltage they are in same phase. We'll see that V is equal to V0 sin omega t and I is equal to I0 sin omega t or sin theta anyway. So these two are both a sin theta, so they don't have phase difference, so they are actually parallel to each other at each point. You can look it here, I think. Yeah, so anyway, we'll just discuss that. So here what I'm trying to say, in case of inductor also we'll represent this two, like current and voltage with two different rotating vector or phasor, and then we'll with a particular angle or specific angle between them. Okay, and from there we will actually be able to find out many other parameters geometrically. Okay, so this is our phasor diagram. So a diagram that represents alternating current and voltage of the same frequency as rotating vectors along with proper phase angle between them is called phasor diagram. Okay, so this phasor diagram we'll discuss again practically how to see the phasor diagram and how we'll be analyzing circuits using phasor diagram. We'll just see as we go along. Okay, so fine. So let us go to the next topic. That is resistor. When a pure resistor is connected, okay, so pure resistor is connected to a AC signal. Suppose this AC source produces signal V0 sin omega t. Okay. So in case of DC circuit, you know, when we connect a battery with resistor in series, so suppose this is positive, this is negative, so current flow, suppose I, so we can write this is R. We can write this I is equal to V by R. Okay, this is Ohm's law. So Ohm's law, using Ohm's law, we can analyze DC circuits, DC electrical circuits. Now we'll see when AC or sinusoidally varying current is passed through that, then how we can analyze. See, in this case, since it is only a resistor connected in series with the source, and there will be a potential difference across this AB, across this R. Okay, suppose the current passing through this is I, so VL will be okay IR. VL is equal to IR. And here, since there is no source of potential like a drop in this particular circuit, so we can say from Kirchhoff's law, from KVL, KVL says VL is VL, sorry. Okay, so VL is equal to V0 sine omega t. Okay, what is this VL? VL is IR. So this I of the instantaneous current through resistor will be V0 by R sine omega t. So this is actually the current, and we can just take this I0 here, this particular term V0 by R I am taking as I0. I0 sine omega t. So what we are seeing here in this case also, see, we have seen in case of DC, this is DC. In case of DC, we use Ohm's law. In case of AC also, we could see that Ohm's law is valid. In case of AC also, the Ohm's law is valid. And what you see in this figure, see, I'll just clean everything maybe. I'll just write two things here. I'll just write two things. What is the current, what is the voltage sent through the resistor? That is V0, V is equal to V0 sine omega t. And we have seen the current passing through the resistor is I is equal to I0 sine omega t. Okay, I0 sine omega t. And so what you see here, see, both are actually varying as sine curve, and also you can see the frequency are same for both. Okay, only difference is the magnitude. See this graphically, it is represented here in this particular figure. Look, the current, amplitude of the current is less than the amplitude of the current of voltage. This is V0 and this is I0. Okay, so amplitude of the voltage is more than amplitude of the current, and you can see both are actually moving with the same frequency. That means, see, they are matching, their maxima and minimas at the minimas are at the same point, since both have the same angular frequency or time period. And another point is that both are, so this means what, when the maxima and minima, when the maxima and minima are at the same for two waves, then it is called that current and voltage, current and voltage, voltage are in same phase, in same phase when a when an AC signal is sent to a resistor. Current voltage relationship here. I'm sorry, I don't know from where it was. So what we have discussed, I'll just recap. So if a resistor is connected in an AC circuit and an alternating voltage V is equal to V0 sin omega t is passed through the resistor having resistance R, we see that the voltage drop across the resistor will be IR if the I is the current passing through the resistor. Actually, this arrow is not for the current, just to show that current is passing. So that is the reason this arrow is given, because there is no definite direction for the current, neither it has a definite direction for the voltage also, because it is changing. So this is this you should not take in another sense. Okay, so since this is a purely resistive circuit and there is no other component to draw potential or to draw voltage from the source, then voltage drop across the resistor itself will be exactly equal to the supply voltage. Okay, so I can write, if the current passing through this circuit, alternating circuit, is a circuit where R is only the component, electrical component, then I can write VL is equal to V0 sin omega t, that is IR sin omega t, and from there you can find out I, the current, probable current through the circuit is V0 by R sin omega t, and V0 by R, this I'm taking as the magnitude of the current in the circuit, that is I0. Okay, so where I0 is actually V0 by R. Okay, V0 by R. All right, so this is the thing, and we see this, these are the expression for the current and voltage through the resistor. V0 sine omega t, this is the voltage from the supply, and the current through the resistor is I0 sine omega t. See, sine omega t, they have both have the same frequency, and also they are in same phase. Same phase in the sense current and voltage will actually have their maxima and minima at the same point at each instant. Look, in this case, see, this is the current, sorry, this is the voltage, this is the current. This green curve is for the voltage, sinusoidally varying voltage, and the red curve is sinusoidally varying current. And see, they are, see, minima, so at 0 they both at 0, at 90 degree or pi by 2 radian, there the maxima are there. Okay, both are actually matching at the same point. Similarly, here it is 0 for both. So that's why they are called current and voltage are in same phase when an AC signal is sent to sent through a resistor. Okay, and see, this thing is actually we have seen analytically, but if we want to analyze this graphically, so how do we do? So relationship, current voltage relationship with Phasor diagram method or with Phasor and Phasor diagram. Okay, so in this case we had seen that V is equal to V0 sine omega t, sine omega t. So this phase factor is same for both. I is equal to I0 sine omega t. Okay, both are sine curve, and you can see they are having the same phase, so that's why, see, they are parallel to each other. Actually, see, they are parallel to each other at each instant. They are parallel to each other, so that's why, see, in any vector algebra, if we know that a vector is parallel to b, what we write? A is equal to some multiplicative factor c b. Okay, some multiplicative factor we just give, or this is actually parallel to each other. And you can see when vectors are actually vectors, parallel vectors can be written like this. So this is the bigger one is a, and this is b vector. Okay, b vector. So they could be represented by two vectors in the same direction because they are in same phase. So two vectors is current. This is the, see, the magnitude of the vector, red vector. Okay, red vector is current. Okay, so it is less actually because you know this is V0. See, current is V0 by R. Okay, and see, the voltage is having the greater length. That means it has greater magnitude or amplitude. Now, if you take the projection, so this projection of this blue tip gives you the V0 sine omega t. This Vm, you should write V0 sine omega t 1. So at an instant t1, see this, at an instant t1, see, this is the one. Okay, so at any instant of time we can get the instantaneous value of the current. That is one thing. Graphically, we need not have this. Okay, and this is how Phasor diagram. See, this a figure A is actually Phasor diagram. Phasor diagram, see how they are represented. They are represented, say, by two rotating vectors with a proper angle. Proper angle means a, see, the vector, current vector and voltage vector, they are actually parallel to each other, so they have zero angle between them. Okay, so this is the way to represent graphically or with the Phasor diagram. Now it will be very interesting when we go for inductor, pure inductor in AC circuit. So if a pure inductor is connected in an AC circuit and a sinusoidally varying voltage V0 sine omega t is actually sent through this inductor, then what happens? We'll just see analytically what happens. Analytically, we know, see, if I say that a current I is passing through this, some alternating current I is passing through the inductor. When an alternating current passing through inductor, that means current is actually varying continuously. And we know varying current, whenever there is a varying current through the galvanometer, there will be a change in the flux, and it will actually produce a back EMF. It will produce the back EMF. Okay, so that back EMF, suppose VL is the back EMF across this. So how do we write back EMF? You know that VL is equal to L di dt. L di dt, because the flux is equal to Li. So d phi by dt with the minus sign, so minus L di by dt. Okay, so this is the EMF which will be actually induced uh, across this coil, okay, across this inductor coil, and this will oppose this particular LDIdt, and this particular quantity, this EMF which is called back EMF, will oppose the flow of the current or oppose the voltage. Okay, so what we can write from Kirchhoff's law? We can write the whole, since it is pure inductor, there is no resistor associated with that, so we can just consider that as pure inductor. So in case of pure inductor, see, there are no, like, there is no other electrical component in the circuit, so I can say VL itself is equal to V. So what is this VL? VL is minus L di dt, and V is what? This V is actually V0 sine omega t. Minus V0 by L sine omega t. Okay, so this is actually the expression. Now see, we need to find out current, right? So we'll write di, integration di. So that is actually minus V0 by L sine omega t dt. So sine omega t dt, when you go for integration, it will be, sine will bring a cos, so omega will be in the down, so omega 0 L, and this will be cos of omega t. I think this will be directly exact equal to this. Okay, there is no need to put sign and all up to here. Now after doing the integration, we get minus sign because cos has come. Look, this, if this is the current is this particular say V0 by omega L, and this is minus cos of omega t. So this minus cos of omega t, what we can write in terms of sine c minus cos omega t could write in terms of sine as sine omega t minus pi by 2. So this is how we can write minus cos phi, sorry, cos omega t. So what we get actually here, see, I'll just rewrite this portion. I'll just remove. You might be thinking, where is the integration constant? Integration constant is actually a sinusoidal varying quantity. So if we take the average of that, that will give you 0. So C1 is the, okay, C1, sorry, C1 is the quantity which is C1 integration constant. Okay, this actually varies sinusoidally. No, this doesn't vary sinusoidally. Okay, when we take average of this, actually we'll get 0 out of it. Okay, so that's why better we write this I equal to I0 sine omega t minus pi by 2. Okay, so this is what we get, and then voltage what was there, V0 sine omega t. Okay, so we have got current and voltage through the capacitor, sorry, inductor, pure inductor. And what do you see here? What do you see here? We see there is a phase difference now, voltage and current. Okay, this is pi actually. So here we can see that current is lagging behind. Lagging behind. Current is lagging behind the voltage by pi by 2 radians, or okay, or 90 degree. Okay, so this is the current voltage relationship. See, if we just see the magnitude, see from the Phasor diagram, if we look here, from the Phasor diagram, what we see? Phasor diagram, see, we have to show that current is actually pi by 2 or 90 degree lagging behind, whereas this is actually leading. So that we are showing here. Look in this diagram. See, the voltage is actually, see, this angle is 90 degrees, isn't it? And this is the current. So this is the phasor of current, this is the phasor of voltage. And see, in case of inductor coil, current is lagging behind by 90 degree. Okay, lagging behind the voltage phasor by 90 degree. So what is the angle between them is actually omega t minus pi by 2. Okay, so this is voltage phasor. This is current phasor. And this is actually current phasor, and I'm not discussing again. See, their instantaneous values will be the projections. So this projection, it is here, this instantaneous value of the current I0, this I0 sine omega t, 1 here it is taken T1 minus omega t, and voltage will be like this B0 sin omega t1. Okay, and they have the angle between them 90 degree. Okay, difference. And you look here, see here, since they have the phase difference and current is actually lagging, so this is actually current is lagging 90 degree by or pi radian by. Okay, so current is lagging behind the voltage by 90 degree. So here, look here, and you look this. So this has actually, so this is actually pi. Okay, this is pi, and this particular is actually, this particular value is actually, so this is negative, so this will be positive actually. Okay, this will be positive when pi. And 2 pi is here, see. Okay, so 2 pi is here. Well, let's see here, one term I just forgot to tell you. See this current I had shown, right? Current integration was like omega 0 by omega 0, sorry, V0. So V0 maximum, sorry, I0 maximum current was given as I0 maximum current is V0 by omega into L. So this 1 over omega into L has a dimension. Sorry, 1 omega, see this is called XL. This is omega into L. This is called inductive reactance. Inductive reactances. This is called XL. XL is called. So this XL actually is acting as a, see, V0 by this particular term is current. That means this acting as a resistor. So acting as a resistor. Okay, a resistor. Acting as a resistor. That's why this particular term omega to L is called inductive reactance. Inductive reactance it is called. Inductive reactance. Okay, so graphically we showed how current and voltage are related in inductor coil, and we have seen that omega L, this is a quantity which is named as XL, which is called inductive reactance. Inductive reactance, I'm sorry, reactance, inductive reactance, and it is a dimension of ohm, or it has a unit ohm. Okay, it has a unit ohm. That means, you know, if you increase the frequency, look, there is a very interesting physics over here. See, XL is omega into L, so it is varying directly proportional to the frequency of the AC signal. So this is omega is equal to 2 pi f. So when frequency increases, then see, we can write 2 pi L omega f. So as the frequency changes or frequency increases, the inductive reactance also increases. That means, again, if this phi is 0, then capacitive reactance is 0. What does this mean? Okay, so XL is 0. XL is 0 at frequency 0 frequency. 0 frequency. That means DC. You know what does this mean? This means inductor coil do not opposes do not oppose. So say I should write does not oppose do not oppose the current. So inductor coil does not oppose the DC current, but it does for AC. It does. It does means it opposes the AC current. So inductor coil actually does not affect the DC current. Okay, DC current. It actually offers resistance to the AC current. Okay. Okay, so this is, so what is the phase angle between them? Phase angle between another point, phase angle between inductor, phase difference between the current and voltage in inductor is pi by 2 radian or 90 degree. Okay, so I think I'll stop it here for today with this. Next day, okay, just one more concept I'll just discuss here. Okay, see here we have got power. If we want to find out average power, so we have got V average power, VI average, right? So here we will get V0 I0 sine omega t, and so this is minus, means we wrote that it is I0 sine omega t minus pi by 2. If we integrate this with dt and integration 0 to t full cycle 1 over t like this, then we'll actually get 0 over here. So why is it so? Because see, the inductor coil in a, suppose this is half cycle, okay, half cycle of oscillation or revolution, whatever you say. So when the inductor is actually absorbing, see, it absorbs energy, electrical energy during 1/4 of the cycle, and then it releases that stored energy during the other quarter of the cycle. Other quarter of the cycle it releases. So thus, if we take the average, like the power taken by or power input by the inductor and relays, if you take the average, so that will individually become 0. Okay, so average power what? Average power dissipated in the pure inductive circuit is 0. Okay, pure inductive circuit is 0. All right, so we'll stop it here for today. In the next class, we'll discuss pure capacitor in an AC circuit and then we'll learn combination LR and CR in combination. Okay, so thank you for your patience. Bye for today.